All right, let's jump right in. Today we are talking about something pretty fascinating, the electrical chaos of an irregular heartbeat. Now this is a problem that affects millions of people, but we're going to look at a really cool model that helps us understand the electrical storm that's actually causing it.
So, you have to wonder, right? What does a chaotic heart rhythm really look like? It seems like a simple question, but the answer is this incredible story told through electrical signals. We're about to look at the hard evidence, the actual signature of a heart in turmoil, and see what it can tell us.
Okay, here's our game plan. First up, we'll dive into what we mean by the heart's electrical storm. Then we'll put two different heart rhythms side by side so you can see the difference for yourself. After that, we'll get into how scientists actually measure this chaos. Then we'll break down the surest sine 2 model, and finally, wrap up with why this whole thing is such a potential game changer.
So our main focus here is a condition called atrial fibrillation. You've probably heard it called AFib. Just imagine the heart's upper chambers, the atria, are in a total state of electrical chaos. So instead of one clean, coordinated beat, you've got hundreds of messy signals firing off all at once. It literally creates an electrical storm inside the heart.
Now, talking about an electrical storm is one thing, but seeing it, that's when it really clicks. We're about to compare two EKG readings, one from a heart with AFib and one with a totally normal, healthy rhythm. Get ready, because you're about to see the chaos with your own eyes.
Okay, check this out. Look at these two EKGs. The secret is in the baseline. That's the line between the big heartbeat spikes. On the right, with a normal rhythm, notice how flat and quiet that line is? That's what they call atrial electrical silence. Now, look left. Look at the AFib EKG. That baseline is a complete mess of what the study calls chaotic micro-oscillations. It's like pure electrical static where you should have silence.
That visual difference is, well, it's pretty shocking, right? But in science, just saying something looks messy doesn't really cut it. We need to prove it. We need hard data. So the question becomes, how do we turn that visual static into a real number?
And this graph, this is the proof. What it's doing is plotting the voltage of that baseline from one beat to the next. The blue line, that's the normal rhythm. See how calm and stable it is? But just look at that red line for AFib. It is all over the place. That wobble right there is the data that proves the electrical instability we just saw in the EKG.
So here's the bottom line. The chaos we see isn't just in our heads, it's real, and it is totally measurable. That baseline isn't just a little noisy, it is quantifiably, significantly unstable. And that instability, that's the smoking gun for atrial fibrillation.
So to put an actual number on that wobble, scientists use a really neat tool called the coefficient of variation, or just CV. You can just think of it as a standardized way to measure instability. A really high CV means lots of chaos, and a low CV means things are nice and stable. Simple as that.
And boom, here is the knockout punch. This chart compares the CV for both rhythms. Look at the box for AFib on the left. It is just dramatically higher than the one for the normal sinus rhythm on the right. And you see those three little asterisks in science? That means this isn't some random chance or a fluke. It is a statistically significant difference. We now have one single number that perfectly captures the essence of all that electrical chaos.
All right, so now let's see how all these different clues, the visual EKG, the hard data, how they all fit together. This is where the surest sine 2 model comes in, because it connects all the dots into one logical, really clear chain of events. This is just brilliant, because it illustrates the whole process perfectly. It starts with atrial fibrillation itself. That condition then triggers a continuous storm of electrical activity. That storm completely wipes out the nice, quiet baseline we're supposed to have, which results in those messy, chaotic micro-oscillations we saw. And finally, all that visual chaos gets measured as one simple thing, an elevated baseline CV. It is a perfect A to B to C map from the disease to a number you can actually measure.
Okay, so we've gone through the science, but what does this all mean in the real world? You might be asking, so what? Why is having a clear step-by-step model like this actually important for understanding something like AFib? Well, it turns out it's a huge deal. This model gives us three really important things. First, it's a clear roadmap for doctors and patients to understand what's happening electrically. Second, it takes a fuzzy idea like chaos and turns it into a hard number, that's CV, which is an absolute game changer for research. And third, and this might be the most exciting part, by identifying such a clear signal, it paves the way for building smarter, more accurate diagnostic tools down the road.
And that really brings us to a fascinating question to end on. We've just seen how a really complex electrical storm raging inside the heart can be boiled down to a single measurable value. So could a simple number, like the coefficient of variation, be the key that unlocks a whole new future of smarter, maybe even predictive heart monitoring? It's a pretty powerful idea to think about.